Hello folks, just doing the audio sync test. While we're waiting, could someone please let us know if you guys are in the chat? If I put the chat in the right thing? Hopefully I did. Are we working with a full second audio delay today? Because that, if so, that's terrible. Close enough. Alright, hello class. Welcome once again to your favorite class this semester, where we're going to talk about assembly programming. Once again. Ba-doing. Cool. So, I think we'll just start from, we'll recap the last couple of slides. Question. The comment delay is even crazier. Huh. Yeah. Well, you know, it is what it is. Yeah, I'm not sure I can actually see the seconds, but interesting. Alright, so, we have been talking about assembly programming. Huh. Yeah. Well, you just gotta, you know, go with the flow. It's frankly amazing that this is even possible, you know, with respect to live streaming and that sort of thing. Like, there's definitely a reason a lot of professors don't do synchronous lectures. And, you know, given all of the technological restrictions, it's amazing anything works at all, so we should be thankful for what we have. Yeah. So, so let's talk about memory interactions with assembly programming. Up to this point, we have been working exclusively with register memory, but other types of memory exist too. So, register memory, obviously, you got these. Let me just pull up a program. There we go. So R1, R2, etc., etc., these are your registers. Registers are, of course, the memory that's contained within the CPU itself. Over the next few slides, we're going to see how to declare and initialize regions of memory, find the addresses of declared memory cells, load data from memory into registers, and store that data from registers back into memory. The key to understanding this process is that only registers may execute data manipulations. C handles these procedures in such a manner that it will look like you are manipulating main memory directly when that's technically impossible. So when you execute an add or a multiply command or a binary or a bitwise XOR or something like that, those operations are hardwired so that they occur between different registers in the memory. they do not occur between different things that are stored in external memory. They have to be loaded from the external memory into the internal memory of the CPU before you can execute those instructions over them. So we're going to see how you do that. So, first of all, let's see how we declare regions in memory in assembly. Let me pull up Visual. There we go. So, in order to declare regions in memory, we have a special type of statement, which is a memory declaration. This declares regions of memory and initializes it. I remember that we did this already, so there we go. If we execute this, boink, emulation complete, tools, view memory contents, you can see that we have, if we view it in decimal, the first one that is at word address 100, and it is 77. Then 4, 8, 15, 16, 23, 42. 4, 8, 15, 16, 23, 42. Notice the address offsets. So, right. If you declare a number of elements here, then you end up with an array. If you declare just one, then you end up with a register, or with a variable. It turns out that at this level, there's not a whole lot of difference between a variable and an array. It's mostly in the matter of, it's mostly whether or not you can, access different indexes. So the numbers that we provide afterwards initialize the memory. These variables may not be used directly to access the data within. There's no in-place dereferencing operator. So you can't use myvar as you would use a variable in C. Instead, you have to use that tag in order to access a memory address. So in order to load data from a declared memory region into a register, you need the following operations. ADR, or address of, the first operand is the register that you're loading the memory address into, and the second operand is the tag associated with the memory you wish to load. So, we also then have LDR, or load register. This loads it loads into the first operand the address specified by the second operand, and that has to be enclosed in square braces. The square braces are roughly equivalent to C's dereferencing operator. So in this, let's just copy this over here. Doop 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 doop. Oh my goodness. Let's get rid of these. There we go. So, you can see that our registers are now loaded with, R1 is loaded with the address of the loaded array, right there, and when you perform the load register operation, it extracts this word value and places it into the register. Once it's in the register, you can use all of the rest of the instructions on it that we've been using so far. But until you've loaded it from the RAM, it's not in a register and can't be operated on. So, in that, let's do some different things here. If we want to work with an array, we take the address of we want to store that in R2, and we take the address of array instead. And let's load. I'm remembering that I did this last time in class, but we'll just continue on. R2. So if you take a look, R3 ends up with the first value of the array, because if you remember, an array in C, like the array identifier itself is a pointer to the first element of the array. This is the same. It turns out that that's actually how the hardware works. So if we want to access any of the other elements, we're going to have to do some manual manipulation. So the way that you do that in ARM assembly is you put a comma inside of the square braces, and then you can either provide it a literal value, or you can provide it a register that contains the index that you want. So if you try just using index numbers in order to do this, you end up with a problem where the address that you're asking for is not actually aligned to your word size. So the take-home message here is that you actually, in order to access the various elements here, you're no longer entering indexes. You're no longer referencing elements in an array. You are directly referencing the word address in memory, which means that you manually have to include the byte offset each time you increment. So rather than doing 1, 2, 3, 4 to access all of the elements in the array, you would have to do 4, 8, 12, 16, 20, because that means that you're actually asking for the specific memory addresses. So 4, 8, F, 10, 17, 2A, those are in hexadecimal, but it's 4, 8, 15, 16, 23, 42. So there you go. That's how you would access array elements. Storing memory from registers into memory requires but a single instruction. It is str R2 R1. Now, the only catch with this particular operation is that the operands are in the reverse of their usual order. We are storing the data in operand 1 in the memory address indicated by operand 2. Normally, we're assigning to, you can think of it as assigning to the first element. In this case, we're assigning to the second. So, let's say we wanted to store in memory into myvar. We would store, let's just say, the literal value of 60, and we will put that in the memory address stored in R0. Oop, we got a syntax error. Not valid. Have I misspelled it? Maybe it wants... Maybe it has to have a register here. Yep, it has to have a register. So literals are not permitted. You have to load the literal into a register, and then you can store that register in a memory address. Yet another slightly arcane manner in which, all of these things have to be done in assembly. That's kind of par for the course. So if you take a look, the value that's being stored in R0 is the memory address of myvar, which is oh, no, sorry, we're looking for R2. R2 is the memory address of the array, which is hex 104, so that gets stored as the data at address 100 by that instruction. There you go. This means that in order to write data into memory, we either need to dedicate a register to holding onto that variable's memory address, and the data that you want to store it also has to be in a register. Or we need to keep loading that address using ADR. So you don't necessarily have to hold the addresses in register memory, but it's for our purposes, it's unlikely that we're going to use all of these. So you can easily just keep them at the back or something, and then bring them out when they're necessary. The alternative is, overwriting the register memory and continuously reloading the address whenever you need it. So, let's start a suitably complicated example. Let us consider the problem of taking the sum of an array. We'll make the following assumptions. Number 1, we wish to sum an array that has been declared in the assembler directives. So, we're not going to be reading this array in from outside. This is going to be, we're going to declare the array inside of the assembly program itself. So this is not quite the same as writing a function, right? This would be like in the same vein as in assignment 1, where you declared variables with initial values, and those initial values were the inputs to the code that you wrote lower down, and then you got outputs out of that. So, the size of the array we are working with is also stored in declared memory. We wish to output the result to a memory address. So, you may have noticed that, in C, it's often necessary to specify what the size of the array is. So, in assembler, it is even more important to declare what the size of the array is. The following declarations will be used. So let's make a new assembly program here. Blurp, 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 blurp. That doesn't actually work. New unsaved changes, you say. Do you wish to save them? No, I do not. There we go. So we have array, which is declared memory, 10, 20, 30, 40, 50. Size is also a DCD, and the size is 20. Notice that the size is in bytes, not in elements, right? These are all integer elements. Integer elements are 4 bytes apiece, so our size will be 20. And of course, we want to leave some space in memory for the result. So that's how we do. If we take a look at the memory contents, there you go. Reasonably straightforward. Incidentally, the only reason these word addresses are being so consistent is because this is an emulator. Next, we need to lay out our registers. So let's say R0 will be the memory address of the array, since we need it throughout to access different elements. So, in that case, ADR address R0 array. R1 will be the size of the array. Since we only need this value to be set once, like a constant parameter, we don't actually need to maintain the memory address of size. We only need the value in it, since we're not going to. Once we have the value out of it, we don't need we don't need it anymore, so we don't need to maintain the memory address. So we can even do address R1 size, and then load into R1 the value at address that's already stored in R1. This will overwrite the address, but it will also load into R1 the value of size. And if we execute that, you can see that R1 contains 20. There you go. To compute the sum, we need an accumulator and a counter. So let's make them R2 and R3 respectively. So let us move into R2 the value of 0, initialize that guy to 0, and let's move into R3 the value of 0 as well. To store the result, we'll need a register for the address of the memory cell that we wish to store the result in. Make that R4. So we will store the address of result in R4. And let's just label this block init. And after that, we will start. So this is code inside of the slides that does roughly the same thing. So far, so good, I hope. Has anybody got any questions about that so far? So, once our registers and data are set up, we can proceed to the meat of the algorithm. Fundamentally, in order to compute the sum of an array, we need to loop over the array until the maximal element in the array is reached. So basically in C, we are trying to implement for int I equals 0, I is less than size, I plus plus, sum plus equals the array at I. And there should be a semicolon there. We know how to, so of the operations that are going on inside of this C code, we know how to increment I, test the condition, and create the loop itself. And we already talked about I, how to do that, but it's in the slides coming up. So what we don't know how to do is read the element of an array at a specified index I. Although, again, I did that already. Because the elements of the array must be loaded from memory, we must use the load R instruction to do so. You can use register offset to dereference a memory address with a given offset. The offset may be a register or a literal, but in this case we'll use a register. Putting that together, we get the following. Load R, R5, R0, R3. So we are, remember, R3 is our index, and R0 is the array. R5 is a new register that we will use to temporarily store the things that are being read from the array. Then we wish to add to our counter. This is our accumulator, and this is our counter. We wish to add the current value of our counter to the thing that was just loaded into R5. This essentially implements sum is plus equal to array at I. And of course, in order to implement the I plus plus, we have to do as follows. Add R1, no, sorry, R3 is the counter, and we will, yeah, so R3 is equal to R3 plus 1. Good. So, let's discuss how to do the loop then. So, when we do this pseudocode, we want to, or the pseudocode, when in the C code that we're basing this off of, we have this comparison. I must be less than size. So, in order to do that, size is being stored in R1, and the counter, which is I, is being stored in R3. So we want to compare R1 and R3. We then wish to branch based on the results of that comparison. So it's really as easy as using the condition codes in the manner that you would expect. So R1, R3, we were wanting to branch on R1 being less than 3 back to the start. There we go. And so let's see if this executes. We'll just save that up here. Array some demo.s. I found out with Visual that if you don't save your work as you go before you execute, if you if you end up writing an infinite loop, which is very easy to do because you're using goto statements, the program will just hang and you won't be able to save your work. So the fix that I found, if that happens, is you take a screenshot of your program and then you can type it back in by hand. But the better procedure is just to save before you execute the code. It doesn't automatically save it before it executes it. There we go. No infinite loops. So if we take a look at what we've got stored in all of these dudes. Testing, testing, 1, 2. Testing, testing, 1, 2, 3, testing, testing. Testing, testing, 1, 2, 3, testing, testing. Testing. Boy, the compression is terrible. Come on, hold it together. Hold it together, the stream. For God's sake. As long as the audio still comes through, that's... Alright. Maybe it's stable again? I don't know. I'm gonna continue. So, now I'm paranoid about the connection. So anyway, we were just in the middle of there's a problem here. So we need to step through it to see what the problem is. So we execute all of these instructions. We've got 10 loaded into R5. We then load. We then add that to the actual accumulator. Yeah, okay. I didn't follow my own rule. So this should be a 4, because it needs to be the size of the byte offset rather than an index. So we got a 4. Now we've got the comparison, and this turns out it's checking. Less than is checking the N and V flags. So let's take a look and see what it is that checks carry. Maybe if we flip these guys. Yes. So it seems like it's this guy less than that guy, which, technically that would, in regular coding, that would look like a greater than rather than a less than. But again, everything in assembly is reversed of what it should be because reasons. So as you can see, what's going on now is that the accumulator is actually accumulating the values in memory until such time as the R3 register, which is our index, acquires the same value as the R1 index, which is the size, in which case the branch statement does not execute, and then we terminate the program. And then cool. Then the only thing that remains is to store the element in the array. So store the element in result. So our element that we are storing is the accumulator, so that would be R2, and the memory location we're storing it in is R4, the result. So we can execute this code, take a look at our memory contents, and you can see that this memory address does have the correct value in it. So there you go. Cool. Any questions about that? I will wait for your questions. point of view, you're the router. Yeah. No, I've got ghosts in my router. I checked it earlier this morning because I was having similar troubles to this on my my 1MD3 stream, and it was it ended up being the ghost of Sean Connery in there. I'm not sure why precisely, but well, it seems as if we don't have any questions. So, so let's just bang out the rest of these slides. This is essentially a listing of the code that we just did in Visual, except it has comments. You know, size of the array in bytes, address of the array, address of the size, then you move it over, etc., etc. All of the stuff that we've done. I named the tags slightly differently in this version. So, again, Visual will show us what our stored memory values are if we select Tools, View Memory Contents. This is what it looks like after the start block, and this is what it looks like on termination. So there you go. And, yeah, it seems... I could have swore there was... Yeah, there's more slides, it's just not... Oh, I see, okay. Alright, so, things of note. Notice how we are increasing R3 by 4 each iteration. In C, we don't have to worry about the data width of the elements of our array. This is taken care of for us by the type system. You may have also noticed that assembly doesn't have a type system. In assembly, the types, it's kind of like how things work in Python. A thing has a particular type because it's used like it has a particular type. You know, sort of irrespective of the bit width problem. Like, obviously certain things of certain sizes can only have certain operations performed on them, like a float needs to have the bit width of a regular float in order for that to work properly. But for example, the difference between a signed and an unsigned integer in assembly code is that you use signed or unsigned operations on it. So there you go. Actually, while we're at it, I think I'd like to show you guys a tool or a web page that'll probably be helpful for you while you're doing Assignment 5. Assignment 5 will have a couple of questions on assembly programming. I don't think they're super difficult, but, you do have to have absorbed the concepts in order to be able to do it. So, in Visual being an emulator doesn't actually implement the entire instruction set for ARM assembly. There are actually some reasonably important exclusions that I noticed when I was constructing the assignment questions. The assignment questions have been constructed to use you can do the assignment questions using only the instructions provided in this list of instructions, the list of supported instructions by Visual. You'll notice that multiplication isn't on this, and neither is modulus, and neither is division, which seem interesting exclusions. The reason for that is that those operations are actually fairly complicated at the assembly level, but, Still, you'd think that they would have included them, but, you know. Again, I'm under the impression that this is, some master's student's project. But, anyway, there are ways of doing multiplication without a multiplication operator. Repeated addition is the definition of multiplication. Ta-da! And there are ways of divide 2 without using division. One of the assembly problems that I've given you guys to chew on is the Collatz conjecture. And in order to compute the Collatz sequence, you have to be able to multiply by 3, add 1. That's like one side of it. And the other side is you need to be able to divide by 2. So if you perform a logical right shift operation, that in a binary system, that is a division by 2. So that is how you can divide by 2. And you can multiply by 3 by adding something to itself 3 times. Or adding something to itself twice. If you start off with a thing, then adding to it twice ends up with, multiplying by 3. But anyway, so there you go. So we have to manually align our pointers to the word sizes in memory. Since integers are 4 bytes in size, we increment by +4 rather than +1. The memory map can verify for you what your word size is for a specified operation. So, and then we have the last slide comic. I realize that, we still have 5 minutes left in the class, but I don't know, if I let class out a few minutes early, I don't think I'll have many complaints from you guys, eh? So, here is the funny. Wasn't my joke about the terribleness of x86 assembly so funny? You can replace ARM assembly for that. Oh wait, you're not a programmer, you wouldn't get it. Actually, most programmers wouldn't get it. Forever alone. Anyway. So, if you guys have any questions, I will hear them now. Maybe you guys are asking questions, but this is just frozen. I'm going to reset it. Nobody's got anything to say? Oh my god. Come on, hold it together, stream. That's a good question, Anthony. Anthony asks, are the assembly questions done in the same way as the C ones in JHub? Does the autograder work with them? No, the autograder doesn't work with the C questions. Well, some of you may believe that. No, the autograder does not have an implementation for the assembly questions. Those are going to get marked by hand, but generally speaking, this is what my expectations are for the ARM assembly problems. I'm expecting you guys to download Visual. I'm expecting you guys to use this as your development IDE. Visual is available for all the operating systems, so there should be no problems there. Um, if it runs in Visual, then when the TA takes your code, copies and pastes it into Visual, and then runs it, then it should work. So I guess the take-home message is that the questions need to be written in such a manner that if they were copied, if the text of your submission was copied and pasted directly into Visual, that it would work. So, since this is assembly code, and since it's going to be marked by hand, I highly recommend that you guys comment your code in in such a manner that the TAs will be able to, if the code doesn't work, maybe at least give you part marks for effort, for, having put something together, and, explaining your process a little bit. But, yeah, no, it's, unfortunately for the TAs, it's going to be a manual mark. Yep. Yeah. So you don't have to worry about how the auto grader is going to work or not work on your assembly code. You just have to worry about whether the assembly code works. I've tried to be very specific in the questions, but you know how it is. I can never anticipate all of the questions that you guys are going to have about the assignments. Yeah, well, anyway, so much for assembly programming. Thank you very much for paying attention to all that, insofar as you did. Tomorrow, we're gonna start in at C++, and hopefully we'll be able to get a reasonable distance into C++ because it's a very interesting language. And yeah, we'll see how far we get with it before the end of the semester. Another question. I received it, but I didn't receive it. Come on. The internet's just being terrible today. Like, honestly. My goodness. And now Teams is just not working. It's been one of those kind of days, you know. well, initializing. Yes, I should certainly hope so. Well, it seems like Team is not going to load, so I guess I'll reply in Teams when it loads. Thank you very much for your time and attention today, folks. I'll see you all tomorrow.